Good morning to everyone. In the last visit, we have already completed up to the reflection part, that is reflection from the spherical mirror. Now we will start the portion of refraction. First we will complete the refraction of the plane interface, refraction from the plane interface, and then we will start the lens and other topics. Okay? Now, first thing that we are going to discuss today is refraction of light. Refraction. It happens both when the light incident on plane interface or the light striking the curved interface. Now, if I ask you, what is refraction of light? Can any one of you tell me what is refraction of light?
The deviation in the path of light when it travels to 1 million kilometers.
If the light ray travels from one medium to another medium but does not deviate from its path, then is it not refraction? Most of the time we are saying that whenever light is traveling from one medium to another medium and there is a change in the path of light, that is called the refraction of light. But this is not the correct definition of refraction of light. Because whenever light ray travels from one medium to another medium, there is a change in speed of the light. And this change in speed is called the refraction of light. Bending is an additional phenomenon if the light falls on the interface obliquely. Then only on entering the second medium there will be a bending. But if the light ray will not fall obliquely, it falls perpendicularly on the interface, then there will be no bending and the light ray will follow the same straight path. But since it enters the other medium, the speed will change by same amount. Now let us consider this is one interface. Suppose there is air, there is glass. And if I consider the light ray is falling like this, and this is the normal, light ray will bend towards the normal since it is traveling from rarer medium to denser medium. Now, if I consider the light ray is falling like this, then it strikes the interface perpendicularly and enters the glass medium. So, this oblique light ray and this perpendicular light ray, while traveling in air medium, they have the same speed. So both have same speed, c. When they enters the glass medium, suppose in glass the speed is denoted by v suffix g. So this oblique light ray speed and this straight light ray speed both are vg. Okay, so change in the speed is by same amount when it enters the medium obliquely or enters the medium perpendicularly. Okay, there is no preferred value of the speed in any particular direction. So this change in speed occurs since the light ray is traveling from one medium to another medium, and this change in speed is the main reason of refraction of light. So don't say that deviation or the bending of light from its path is called the refraction of light. It is only the change in speed when light ray travels from one medium to another medium. Okay? So write down this one. Change in speed of light. Change in speed of light when light ray enters one medium from another medium. Enters one medium from another medium is called refraction. Okay. Now see the diagram. If it strikes perpendicularly, there will be no change in path, only the speed change. If it is striking obliquely, then there is a change in speed as well as there is a change of direction. So direction change is an additional phenomenon. It may occur, may not occur, but speed change will always occur when it travels from one medium to another medium. So this is the primary reason for refraction of light. Now, if I consider this angle is I, then this angle is represented as R, called the angle of incidence and angle of refraction. Okay. Now, this light ray, suppose A, O, B, and this normal is taken N, O, N prime. Now, just as reflection, there are two laws of refraction. One is saying that incident ray, refracted ray, and the normal lie on the same plane. Which plane? Plane of this board in this diagram, because this is the interface. Because this line like this is the interface. Suppose this one entire is glass, this one is air. Light is striking like this and goes in. Okay, so this surface is the plane, not the plane surface of the medium. It is a plane perpendicular to the interface. That is the plane of this board in this diagram. In that plane, all the three rays lie. Okay. Like in case of reflection, when we say that reflected ray, incident ray and the normal lie on the same plane, it is not the plane of the mirror. It is the plane perpendicular to the plane of the mirror, in which all the three rays lie. Now, there is another law that is called the Snell's law, which relates this angle of incidence and angle of refraction. It says that sin I is directly proportional to sin R. Sin I is directly proportional to sin R. And then this proportionality constant is called the refractive index of the medium. 2 with respect to medium 1. That is sin I by sin R. If you consider this is medium 1, this is medium 2, so we can write this is equal to, initially you can write this is equal to ratio of the speed in these two medium. If we write generally, that is sin I by sin R equal to V1 by V2, where V1 is the speed of light in first medium and V2 is the speed of light in second medium. Then we can introduce the speed of light in vacuum as C and write this expression as C by V2 divided by C by V1. Check. By introducing that constant velocity of light in vacuum, we can write this expression as C by V2 divided by C by V1. Now C by V2 can be written as mu2 and C by V1 can be written as mu1, because refractive index, absolute refractive index is defined as speed of light in vacuum by speed of light in a particular medium. So C by V2 means refractive index of the medium, absolute refractive index of medium 2. C by V1 means absolute refractive index of medium 1, which can also be written as 1 mu2, that is refractive index of medium 2 with respect to medium 1. Refractive index of medium 2 with respect to medium 1. You can also relate these two directly. That is refractive index of medium 2 with respect to medium 1 means speed of light in medium 1 by speed of light in medium 2. Okay. Absolute refractive index means when the refractive index of any medium is measured with respect to vacuum or air. Now suppose medium 2 is glass, medium 1 is water. Then we are saying it relative refractive index, that is refractive index of medium 2 with respect to what? That is refractive index of glass with respect to water, like this. Okay. Now, one problem. Write down. Refractive index of glass with respect to vacuum is 3/2, and that of water with respect to vacuum is 4/3. Then find the refractive index of water with respect to glass. Then find the refractive index of water with respect to glass. What we have to find out? We have to find mu, whose refractive index is to be determined, refractive index of water with respect to glass. So which medium is your second medium? Water. 1 mu 2, refractive index of 2 with respect to 1. So here, whose refractive index is to be determined? Water. So water will be your second medium and glass will be the first medium. Okay, so G mu W, that you have to find out. Now 1 mu 2 means mu 2 by mu 1. So G mu W means mu W by mu G. Just put the value. Mu W is given 4 by mu G is given. So the answer will be 8 by 9. Remember, in the symbol of mu, 1 mu 2, this stands for refractive index of medium 2 with respect to medium 1, and its formula means mu 2 by mu 1. So when we have to find out refractive index of water with respect to glass, then water is considered as the second medium, glass is considered as the first medium. Then we have to find out G mu W. So G mu W will be mu W by mu G. According to that formula, 1 mu 2 means mu 2 by mu 1. So G mu W means mu W by mu G. If I ask you to calculate the refractive index of glass with respect to water, then the answer will be 9 by 8. Okay. So always remember this form. This This will remind you that second index is the medium whose refractive index we want to calculate, and first is the medium with respect to which we are calculating that refractive index. So the formula comes mu 2 by mu 1. So in this case 2 is W, 1 is glass. So we write mu W by mu G. If it is W mu G, then we write mu G by mu W accordingly, and then we will get the inverse of this result, 9 by 8. Clear? Okay. Now, from this Snell's law, we have to discuss one more point. For optic incidence, we have defined Snell's law, and we have defined refractive index from the Snell's law quite easily. Now, what about normal incidence of the light? In the case of normal incidence, when light fall or light incident along this, then what is the value of angle of incidence? 0 degree. What is the value of angle of refraction? So both 0. Now, what will be the value of this 1 mu 2 according to Snell's law? Sin 0 by sin 0. That is 0 by 0. 0 by 0 is 0 by 0 is 0 by 0 0. Okay. Fine. Suppose you are very hungry. One of you is very hungry. Okay. No food is given, and he is locked in a room. No food is there. So after 1 hour, he is still hungry. Another case is there. He is in a room, very hungry, and in that room there is a buffet arranged, and in that buffet there is almost 20 delicious food, all of which he likes very much, and he can't decide which one to start with. 1 hour goes. He is still hungry. He cannot decide which one to start with. Okay, the same thing happens with this case. Suppose I write 1 by 0. What is its value? Again? Undefined, not infinite. Undefined means if you write suppose 10 by 2, that result is 5, we know. Because if you multiply 2 with 5, you will get back 10. Now here, which number I have to write here, which multiplied by 0 will produce 1? I don't know. So that's why the name is undefined. Infinite means a very large number. But any large number you can put, when it is multiplied by 0, it will never produce 1. So any number, 1 or 2 or 4 or anything, multiplied by 0 cannot produce that number. So the result is, we don't know. This is a complete void called undefined. But the same case is not there when we calculate 0 by 0. Because I can put here, which multiplied by 0 will produce 0. But again the problem generates. I can write 0, I can write 1, I can write 1 by 3, I can write root 2, I can even write any imaginary number, anything I can write. Because everything multiplied by 0 will produce 0. So both are undefined. Both situations are undefined. First one is like that, he is hungry and no food. Second one is that he is hungry, there are all foods are, but he cannot decide. So all numbers are there, but there is no unique choice. So both statements will lead you to undefined condition. Okay, so when in the Snell's law you get 0 by 0, that is not 0. 0 by 0 is undefined. Clear? So now it shows that refractive index calculated by Snell's law when the light incidents perpendicularly will become undefined. But can it happen? Because we know normally that refractive index is ratio of the speed of light. So if you consider first medium is air, second medium is glass, and you consider the light is falling perpendicularly, you will get this 1 mu 2, that is A mu g, undefined according to Snell's law when light falls perpendicularly. But normally we know that A mu g means speed of light in medium 1 by speed of light in medium 2. So if it is glass and air, upper medium 1, medium 1 is air, then I can write the speed of light v1, that is equal to simply 3 into 10 to the power 8 meter per second. Speed of light in second medium glass, that is 2 into 10 to the power 8 meter per second, and immediately we can write the result is 1.5. Because speed of light in any medium we know, in air or in glass, speed of light is known to us, and we just divide and find the value of mu. But Snell's law shows that this value for oblique incidence will become undefined. So which one is incorrect? Is Snell's law fails to predict the refraction in this situation, or the calculation of refractive index is wrong? Both are correct. Actually, the undefined thing that you get is just a mistake, because you are putting I equal to 0 or equal to 0. You have to put I tends to 0 or tends to 0, because that is a limiting condition. Because if you consider I is 0, in that Snell's law you are considering only one light ray. And in the last session we have discussed that single light ray is just an imagination. We cannot derive a single light ray. Whenever the light ray will come, there are many light rays, and any of the light ray has the non-zero angle. And as a result, Snell's law is still true. In that situation, only you have to consider the limit. Okay, so remember this one. If someone says that Snell's law is not true for perpendicular incidence, so the answer, this statement is wrong. Snell's law is true. Okay, now so we will move forward. That from this we have to discuss some particular cases of the application of the Snell's law and this law of refraction. First one is lateral displacement. Lateral displacement. What happens in this case? We consider a rectangular glass slab. Rectangular glass slab means two opposite faces are parallel to each other. It may not be rectangular, it may be parallelogram shaped, but two opposite faces should be parallel. Then we call it generally rectangular glass slab. Now, On this, a light ray is incident obliquely at the first interface. So light ray is here traveling from air to glass. Outside medium is air, it is traveling from air to glass. Now, this light ray strikes here because it is bent little bit towards the normal, because it is traveling from rarer to denser medium. Another normal. This light ray will now bend in this direction away from the normal. First it is bending towards the normal, then it is bending away from the normal, because in the second refraction it is traveling from denser to rarer medium. Okay, this angle is called the angle of incidence, and this angle, which is actually the angle of refraction for the second surface, is written as I2, called the angle of emergence. Angle of emergence. Okay. Now, this medium is air. This is glass. This is again air on this side. And if you extend this one with a dotted line, you will find that this path and this path are parallel to each other. The path of the incident ray and the path of the emergent ray, these are parallel to each other. Means there is no angular deviation produced in the path of the light due to this glass slab. This glass slab only shifts the light parallel to itself. Only shift the light parallel to itself. This phenomena is called lateral displacement. Lateral displacement. Okay. Now, how can we prove that this incident path and the emergent path are parallel to each other? If someone asks you that I don't believe that this light ray will parallelly shift to itself, proof. Give me a proof. How can we prove that these two paths are parallel to each other? You have to prove then I1 equal to I2. Means angle of incidence and emergence are equal. Try to prove that I1 and I2 are equal. You require only the concept of Snell's law and little bit of geometry. Angle of incidence for the second surface are equal, because this R is the angle of refraction for the first surface and this R is the angle of incidence for the second surface. These two are equal. Then apply Snell's law for this first refraction. I can write sin I1 by sin R, that is equal to mu G by mu A, that is refractive index of second medium by refractive index of first medium. Here second medium is glass, first medium is air, because light is traveling from air to glass for first refraction. Okay. Now go to the second refraction. What is the angle of incidence? R. So I write sin R. What is the angle of refraction? I2. It will be sin I2. This will be mu 2 by mu 1. Now what is mu 2? Air. Second medium is air now. First medium is glass. Because for the second refraction, light is traveling from glass to air. So we write mu A by mu G. That is equation 2. Multiply equation 1 and 2. Multiply both sides. It will be sin I1 by sin R into sin R by sin I2. That is equal to 1. Because mu G by mu A into mu A by mu G, that will cancel. 1 sin R cancel. So you will get sin I1 equal to sin I2, which implies that I1 equal to I2. Okay. Now something difficult. We have to, I will derive that, but you have to remember only the final formulas. 2 formulas I will mark, and you have to remember those 2 formulas for the solving of the problem. Detailed derivation technique is not required for your exam. So I will solve the entire thing once, because such that you can find out the logics where how to come to this conclusion. But only you have to remember 2 formulas. Okay, 2 to 3 formulas you have to remember from that calculation. See, if the thickness of the slab is given, then from this experiment we can find the displacement of the light ray path, means gap between these 2 parallel lines, that we can calculate. Or if I can measure the displacement experimentally, then I can find the thickness of the slab. Then we can find. Means one has to be given, then the other you can find out. Either slab thickness is given, then you can find the displacement, or you have to measure the displacement, then you can find the thickness of the slab. Okay, so we will discuss that part. This portion is clear? So I will redraw this diagram once again. See. Let's go. This angle is considered as I, because we have already proved that I1 and I2 in this case are equal, so I will write both as I. Similarly, this one is R, this one is R, thickness is suppose T, and the displacement is considered as D. Displacement of the path is D, thickness is D. Okay. Then we have to find a relationship between T and D in terms of angle of incidence and mu. And suppose refractive index of glass is given mu and refractive index of outside medium is given 1. Because air has or vacuum has refractive index 1. So mu 1 is taken as 1 or mu air is taken as 1 and mu g is taken as mu only. Okay. Now, see how to find the relation between T and D. So first we have to increase this normal and intersect it here. And from this point we draw a normal on this dotted line. We draw a normal on this dotted line. So this angle is also 90 degrees. Now we put certain lengths A, B, C, D. Okay. A, B, C, D. I want to calculate this one, AB by AC. Tell me, with respect to angle R, if I write AB by AC, then it will be which trigonometric ratio? With respect to this angle R, I'll take AB by AC. Then it is base, and this one is hypotenuse. Base to hypotenuse is cosine. So it will be cos R with respect to this angle. Okay? So it will be cos R. Cos R. Now, come to the other triangle. Other triangle is ABC. That is also a right angle triangle. Now, I will denote at different angles. Can you tell me what is the value of this angle? I minus R. Because this entire angle is I, so this entire angle is I. This part is R, so remaining part is I minus R. Now with respect to this I minus R, I want to write these ratios. That is BC divided by AC. Tell me which trigonometric ratio? BC by AC. With respect to that angle, I minus R. Sin I minus R. Because with respect to this angle, this one is perpendicular and this one is hypotenuse. So it will be sin I minus R. Okay. Then, if I divide these two, divide second one by the first one, then we write BC by AC divided by AB by AC, that is equal to sin I minus R by cos R. sin I minus r by cos r. Okay. Then AC will cancel. What is DC? Small d. That is the displacement. And what is AB? Thickness. That is T. So multiply this T on this side and you can write T sin I minus R by cos R. So once we know I and R and T, we can find the displacement, or vice versa. That means if you know I, R and T, you can find thickness T using this result. Okay. So mark it as the number 1. This formula you have to remember. Because if the problem comes, you have to remember this formula and directly put the values to find the answer. There is not that much time that you will derive in graph and then solve. So T equal to T sin I minus R by cos R. Okay. Now, see, if I is given, R is given, and T is given, you can find T from this formula, no issues. But if these values are given, suppose it is given that angle I is, say, 30 degree and mu is 1.5 for glass, and suppose thickness is given, T is given, say 5 centimeter. Then how to find T? If I and R given, I given, R given, T given, you can find. In here it is instead of R, the value of mu is given. You probably say that, okay, no issue. I can find for the first point A, I will write Snell's law. Sin I by sin R equal to mu. So I write sin 30 by sin R equal to 1.5. From that I can calculate the value of R and then substitute. But remember, you have no calculator. You have no calculator. In that case, what comes? It will become sin 30 by sin R. It is coming 3 by 2. So it will be 1 by 2 sin R sin R equal to, definitely it has some value, but you don't know. It is not along in any standard angle. So though this formula is correct, but you may find difficulty in solving. Okay. Otherwise, definitely you can do it. How? From the sine r, you have to use to find cos r. Then sine I minus r can be written as sine I cos r minus cos I sine r. Then you have to put. But in the exam hall, you have not that much of time to manipulate all these calculations. So we have to derive something and such that we can remember that formula and directly put the value. If it is given in terms of I, mu and thickness. Clear? See how. I can write this one as t equal to t into sin I cos r minus cos I sin r divided by cos r. Sin I cos r minus cos I sin r divided by cos r. Then this is t into, first term is sin I, second term is cos I into tan r sin r by cos r. Okay. Now, the I is given, mu is given, but R is not given. So I have to find the value of tan R in terms of I and V, such that we get the final formula. How? I have to find tan R. For the first part, I can always write for the first refraction sin I by sin R, that is equal to mu. From this, can you find out the value of tan R? You have to find out the value of tan R from this formula in terms of sin I and mu. Then we will get directly the final formula. This is Snell's law for the first interface.
Can either mean. Can either mean.
I have to find out the value of tan R. Sin R is there in the form. See, can I write this one as can I write 1 by sin R means cosec R. Cosec R equal to mu by sin I. take a square on both sides. So cosec square r equal to mu square by sin square I. One plus cot square r. Then cot square r equal to mu square minus sin square I divided by sin square I. I take this minus 1 on that side and subtract. So it will be mu square minus sin square I divided by sin square I. Okay. Then I take a square root and inverse. Cot square r, its square root will be cot r, and inverse of cot r will be tan r, which I require. So the value of tan r we can find actually. And then this value of tan r we will substitute in that calculation in just the previous page's calculation, this one. So it will be t into sin I minus cos I into sin I by root over of mu square minus sin square I. And one sin I can be taken common. Then you can finally write t sin I into 1 minus cos I divided by root over of mu square minus sin square I. This final form is equation 2. You have to remember this step. This is 1. This final step, t sin I into 1 minus cos I divided by root over of mu square minus sin square I. Such that if mu is given instead of r, you can directly apply this formula and solve the problem. Otherwise, if you are going for this manipulation in the hall, exam hall, then it will be too time consuming. T sin I into 1 minus cos I divided by root over of mu square minus sin square I. Okay. Now, if it is given that angle of incidence is very small, angle of incidence I is very small, then we can make some approximation that I tends to 0. If I consider I tends to 0, then sin I will become I and cos I will become 1. Cos I will become 1. So the final step is this one. If I tends to 0, then sin I tends to I, cos I tends to 1. And in any calculation, if I square comes, this will become, this will also tends to 0. I is very small, so I square onwards I can consider to be 0. Okay. Then that formula for t will become t. There is a sin I. In the previous page you have written formula number 2. Sin I. That sin I will become I. 1 minus. Cos I will be there. Cos I will become 1. Inside the root, first term is mu square, second term is sin square I. Sin I will be converted to I, then sin square is there, so it will be I square, and I square is also okay. Sin I tends to I, and when we do sin square I, it will be I square in that case, because that term is sin I whole square actually. So since I is very small, sin I will become I. So it will become I square, but I square is also negligible, so this term tends to 0. So it will become t into I into 1 minus 1 by mu. This is the final formula 3. So these 3 formulas you have to remember from this problem. So when you will write only these 3 formulas along with the diagram, entire derivation is not required for your revision. You can write only the diagram, draw the diagram and write these 3 important formulas, because all the problems which can come from this lateral displacement can be solved from these 3 formulas directly. Okay. So this is the lateral displacement part, and now we will come to the other part, that is another case of the refraction of light, that is real depth and apparent depth. You probably face many of the problems of real depth and apparent depth. There is a problem that you are looking through a bubble which is stuck inside a glass slab. From one side it looks at a distance of say 7.5 centimeter, from another side it looks at a distance of 3 centimeter. What is the actual thickness of the slab that you have to calculate? So that is based on this lateral displacement. It is based on the real depth and apparent depth calculation. So real depth and apparent depth calculation is another important part. Okay. See. Let us consider this one is an interface, and below this interface This is water we consider, and here we consider it is air. So for air I consider the refractive index as 1, and for water I denote the refractive index as mu. Okay. So mu1 is considered as mu and mu2 is considered as 1. Here I consider water is the first medium because I will consider the object in the water medium and observer in the air medium. So light is coming from water to air, so the first medium is water. If the light is coming from air medium inside the water, suppose some fish is inside water and he is seeing the outside world. So light is coming from air to water, in that case first medium is air and that is considered as one medium 1. But here I will consider a separate situation. Suppose there is some object, maybe a coin inside the water. So from this coin, this is the object, so light is coming and someone is trying to see this coin who is in air medium. This is the problem. Now, see. First, we consider a light ray which is strike incident on the water air interface perpendicularly. So this light ray will not deviate from its path, it will go straight in the air medium. Go straight in the air medium. Fine. We consider another light ray. One more light ray which strikes this medium obliquely and goes into the air medium. So it will definitely bend from its path. We consider it normal at the point of incidence. Okay. We draw a normal at the point of incidence. So this second light ray is traveling from denser to rarer medium obliquely, striking the interface. So this light ray will bend away from the normal when enters the air medium. Now, this angle for this light ray is the angle of incidence, and this is the angle of refraction. Angle of incidence and angle of refraction. If this angle is I can write this angle is also I. See? Because these are alternate angles. Now, by dotted line, I extend this path. This path is extended using this dotted line, which is intersecting this original perpendicular line at this point. Okay. So if this angle is R, I can consider this angle is also R because they are corresponding angle. So corresponding angles are equal. So if that angle is small r, then that dotted line with the blue vertical line will also make the same angle, smaller. Okay. Now, this point is the position of the object. But the man whose eye is here, he will find that the position of the object is here. So what he is actually seeing? He is seeing the virtual image of the object O at point O prime. Virtual image means both the lines intersecting at point O are not the real light path. Only blue one is the real path. The green one is the dotted line, means it is traced there. It appears to pass from that point. So the image is virtual in this case. Okay. Now, let us consider this point is A, this point is B, this point is C, this one is D, this one is E, this one is F. Okay. Now, at point C, I can apply Snell's law for refraction and write sin I by sin R, that is equal to mu2 by mu1 sin I by sin R. At point C, I apply Snell's law, sin I by sin R, that is equal to mu2 by mu1. But what is mu2 in this problem? 1, and mu1 is mu. So sin I by sin R becomes 1 by mu in this case. Okay. Now, come to the triangle OBC. This one is a right angle triangle, where angle B is the right angle. So from triangle OBC, can you tell me what is sin I? It is BC by OC. It is BC by OC. Similarly, take the triangle O prime BC, that is also right angle triangle. O prime BC, the small triangle, that is also right angle. So from that triangle, tell me what is sin R? BC by O prime C. So it will become O prime C by OC, that is equal to 1 by mu. So what is O prime C? It is called apparent depth, and OC is called real depth. So we got the correct formula, real depth by apparent depth equal to 1 by. See, though it gives us that real depth by apparent depth equal to 1 by mu, but you cannot argue from this step, because OC, O prime C, these are not depth, these are the slant heights. Depth means OB and O prime B. Real depth is OB, perpendicular distance should be taken as the depth, not the oblique distance. Then I will immediately write, okay, O prime B by OB, that is equal to 1 by mu. How can I write that? Instead of O prime C, I write OB, O prime B, and instead of OC, I write OB. Because all those hypotenuses are replaced by base, I replace them by base, claiming that the result remains unchanged. You cannot say that these are similar triangles. Triangles are not similar. Then On the basis of which logic I can do that?
Uncle, I should be very small.
Yes?
Uncle, I should be very small.
This I and R, this should be very small. Why this should be very small?
So it will get very close to that.
Who is seeing this object? This man. And this man sees that from air medium, he predicts that object is not here, object is here at point O prime. So the man who is visualizing all these phenomena to his field of view of I, both the light ray CF and BA must enter. In the man's field of view of I, these two light rays must enter such that this man can realize that the object is not at O, it appears to be shifted to O prime. Now what is the size of our field of view? Very small. Field of view means not even the entire eye. The small portion of the pupil through which light enters. So this A point F and point A cannot be at 1 foot distance. This should be very small, less than 2 millimeter almost. So if F and A, these two are very small, then B and C are almost overlapping. That's why we can replace OC by OB. That is the logic. And since our field of view is so small, I can consider all those rays should be paraxial. Otherwise, these two will not enter in our eye. Okay, so if you are here, it is not possible. You should be here. So these two lines should be very close. Then you can only see this one. Otherwise, not possible. At the same line, you cannot visualize the object. Okay. Field of view of a human eye cannot be that large. That is very small. So for that, point B and C should be almost overlap. That's why I write this almost equal symbol. Okay. So in that case, O prime B by OD will come. It will become 1 by mu. Then O prime B means apparent depth and OB means real depth from the water surface. So we can get the formula that apparent depth equal to real depth by mu inside the denser medium. So anything inside water, when we see from outside, it appears to be shifted up. So real depth is less than the original depth. Sorry, apparent depth is less than the real depth. Now sometimes it may be asked that calculate the shift of the light ray. Calculate the shift of the object. So we have to find this O prime distance. That means actually we are calculating d real minus d apparent. Okay, d real minus d apparent. So we have already calculated d real by mu. So it will be d real into 1 minus 1 by mu. This is the shift of the image with respect to the object. So the man sees that this much height is raised by the image. Okay. That means if the object is in denser medium and you are looking from air medium outside, that is a rarer medium, it is always appeared that the object is shifted up. So real depth is greater, apparent depth is smaller. But the reverse phenomena can also occur. If you are inside the water medium and looking outside, suppose at a bird, you are inside and looking outside at a bird which is at a height h, so that is the real height. But inside water, if you try to find out the position of the bird, it will be increased, because now you are looking from denser to rarer. So if I write real height, it will be, apparent height will be mu times real height. In case of depth, it is decreased, but in case of height, when you are looking from denser medium to rarer medium, in that case it is increased. Apparent height will be larger. Suppose the bird is at a distance of 10 meter, but you feel that it may be greater than 10. But here, the object is at a depth of 10 meter, you will feel that object is not at that much depth. Suppose 9. So the reverse phenomenon occurs when the observer is in the denser medium. So remember, in which medium observer is there, that is important for this calculation. If the observer is in rarer medium and the object is in the denser medium, then you are calculating the depth. So we write real apparent depth equal to real depth by mu. But if the observer is in denser medium and the object is in rarer medium, in that case we are calculating height. In that case, apparent height will be increased. So it will be mu times real height. Okay, this phenomena illustrated by a problem that suppose some birds are there, suppose kingfisher or seagull, anything. They are looking towards the fish inside the water. Okay, suppose the fish is at a depth of 5 meter. Then according to this bird, this fish is not at depth of 5 meter. Bird sees that the fish is slightly shifted up, maybe 4 meter depth. But at the same time, when this fish observes the bird, suppose the bird is at a height of 5 meter above the water surface. Fish thinks that the bird is at a distance of suppose 6 meter above the water surface, because from the point of view of the fish, bird is at a longer distance. Okay. So this portion may have some problem in the exam from this portion, and this portion's problem are easy, comparatively easy and formula based, and little bit of geometry is required to solve this problem. And if you remember this type of cases, that is, if the observer is in the rarer medium and he observes something in the denser medium, then the apparent depth decreases. If the observer is in the denser medium, object is in the rarer medium, then apparent height increases. So if you remember these small things, you can solve this topic's problem easily. Okay. So next we will discuss the total internal reflection, and another is fish eye view. That is, if a fish is inside water, then looking to the outside world, then how it looks to that fish. The same thing occurs when we are diving inside water and looking upward. The same thing, that is called the fish eye view problem. Okay, take a small break. Microsoft Paint. Digital paint तो मोटी ओके एक्चुअल नहीं पहुंचे one student is not there. Oh, what happened? Oh. Sorry. See. Suppose this one is a interface of the two optical medium. What happened? This is the denser medium, this is the rarer medium. Okay? Now we consider a monochromatic light. Monochromatic means single color. Light is falling on the interface. Like this, and this light ray will bend away from the normal. So this is the angle of incidence, this is angle of refraction. Okay. Now, if I increase the angle of incidence in the denser medium, then the angle of refraction in the rarer medium will also increase. And finally, one time will come when for a particular angle of incidence, the refracted ray will become parallel to the interface of the two media. That is, the value of R will now become 90 degrees. So there is a particular value of angle of incidence in the rarer medium for which the value of angle of refraction will become 90 degrees and the refracted ray is parallel to the interface or grazes along the interface. Okay? Now, means we can write if I equal to some theta c called the critical angle. This particular angle of incidence is named as critical angle for this pair of media and for a particular wavelength of light. Theta c. Then R equal to 90 degree. R will become 90 degree. Now, since I consider this is denser medium, I consider its refractive index as mu1 equal to mu. This is considered as the denser medium. Suppose class. So, refractive index mu1 is taken as mu. Second medium is considered as air. So, its refractive index mu2 is taken as 1. Okay. Then we consider Snell's law. Snell's law says that sin I by sin R equal to mu2 by mu1. Now what is I in this particular case? Theta c. So I write sin theta c sin 90. Now what is mu2 in this case? 1. And mu1 is considered as mu. So this sin theta c will become 1 by mu, or you can also write theta c equal to sin inverse of 1 by mu. This is the critical angle for the pair of media and for a particular wavelength of light. Now remember, if any member of this medium, pair of medium changes, then the critical angle will change. Not even if the mediums are same, only the color of the light changes, means its wavelength will change, so mu will change, and as a result critical angle will change. Means for a particular pair of light, pair of media, light is traveling from glass to air, you are taking different monochromatic light, suppose green, yellow, violet, blue, red. For all these different colors, critical angle will have different value, because mu depends on the wavelength, and due to wavelength different colors will come. So different colors have different wavelength, so the value of mu will change. Okay, so either you change the medium or you change the color. In both the cases, the refractive index will change, and as a result, the value of critical angle will change. So critical angle depends on the factors, that is the member of the media, pair of media, and the wavelength of light. Okay. Now, if the angle of incidence in the denser medium is increased further beyond critical angle, what will happen? Suppose this one. So the angle of incidence is more than critical angle now. In this case, you will find that the light ray will bend more, and it will enter into the denser medium again. It will not at all go to the rarer medium. From the boundary, the light ray will bend inside the denser medium as if a reflection. Okay, and the law of reflection is again obeyed by this light ray. Means if you calculate for this light ray, this is also I. This angle of incidence is I greater than critical angle. This angle of refraction is also equal to I. That is I equal to I. The law of reflection is again obeyed by the light ray. But there is a special phenomenon. Whenever light strikes an interface, a part of light is reflected and a part of light is refracted. But in this case, there will be no refracted light ray in the rarer medium. There will be not a single part of the light ray in rarer medium. The entire light from the interface is bouncing back inside the denser medium, as if it is trapped inside the denser medium. So this kind of reflection is called total internal reflection of light. Total internal reflection, because generally if you consider normal case, that is, this is an interface, light is falling at an angle less than critical angle. Suppose this I is less than critical angle. What will happen? A part of light will be reflected. It is considered denser, it is rarer, and a part of light will be refracted. What part are there? When angle of incidence is less than critical angle, a part of light refracted, a part of light reflected. But when angle of incidence is greater than critical angle, entire light ray is reflected back. There will be no refracted ray at all. So this phenomena is called total internal reflection. And remember, total internal reflection will obey all the law of reflection. Means I equal to R, incident ray, reflected ray, and the normal lie on the same plane. All these laws are obeyed also. Only the refracted ray becomes vanish. Okay? So the necessary condition is that angle of incidence in the denser medium should be greater than critical angle. Then only total internal reflection will occur. And remember, light should go from denser to rarer, not from rarer to denser. Okay. Now, so on the basis of this total internal reflection, we will discuss a particular problem. See. Suppose this one is a water tank in which up to a certain depth water is filled. Suppose this depth is H, filled with water. Now we consider a source of monochromatic light is here, just at the midpoint at the bottom. There is a source of monochromatic light. So from this the light ray will come and it will propagate in all possible directions. Now, through the surface of water, the light rays will come out. Through the surface of water, light rays will come out. And suppose you are in the air medium and observing the surface of water through which the light ray is coming out. Through which the light ray is coming out. You will see that there is a luminous circular patch. Luminous circular patch formed on the surface of water through which light is coming out only. Remaining portion of the surface of water will remain dark. Through them, no light ray will come out. First, you have to tell why. Why a luminous circular patch is formed? Why light cannot come out through the entire water surface? As if there is a circular hole through which light is coming out. Remaining portion is not opaque, it is completely opaque, and through that light cannot come out. Why this circular luminous patch will form? Why light cannot come out through the entire surface of water? If I evacuate the water in the tank and only the point source is at the bottom, then light is coming through all the surface. But as soon as water is filled up to a certain height, you will find that the light is not coming through the entire surface of water, only through a small portion light can come out.
reflection, sir?
Total internal reflection occurs in this case. Why? See, from this point, light rays will fall on the water surface, water-air interface. Light ray will fall. Let us consider this light ray will fall on the water-air interface. This is the incident light. Now consider a normal at this point. When this light ray, in which condition this light ray can go in the air medium?
When the
If this angle of incidence is less than critical angle, in that case light ray can go from denser medium to rarer medium. But if this angle of incidence is greater than critical angle, then light ray cannot go because it will suffer total internal reflection. And if this angle is exactly equal to the critical angle, then light ray will be going along the surface of water. So we consider this angle is the boundary and it is equal to that critical angle. So we can consider that any light ray falling here can definitely come out because their angle of incidence is less than critical angle. But any light ray which is falling here, for them angle of incidence is greater than critical angle. So those light rays will suffer total internal reflection. Because if I consider this is critical angle, this light ray, definitely this angle of incidence is greater than critical angle. So if this is greater than critical angle, this light ray will reflect it back. So with this boundary we can consider a circular path over the surface. Then I will erase this portion. So we can now say that on this side you can also consider the same thing. So over the water surface, because water surface is there and this is the point source, and then this is considered as the critical angle. Then not only on one side, see, like this. So all the light rays which will travel to this boundary of the circular patch will strike the interface at critical angle. So the light ray which has an angle less than critical angle means within that circular patch those light rays can come out after refraction. But the light rays beyond this circular boundary will have an angle of incidence greater than critical angle and they will suffer total internal reflection and cannot come out. That's why this circular patch is formed. Okay, now so how to calculate this one? I will consider this vertical line. What is the length of that line? H. I consider radius of this circular patch is R. So this side is the hypotenuse, can be written as R square plus H square, because this is perpendicular. R square plus H square. If this angle is theta c, then according to the diagram this angle is also theta c, alternate angles. Then come to this diagram, write sin theta c's formula. Sin theta c equal to 1 by mu, where refractive index of this water is considered as mu, outside medium is air, refractive index 1. So sin theta c equal to 1 by mu. Then consider this right angle triangle and write sin theta c. What is sin theta c? Perpendicular by hypotenuse. With respect to this angle theta c, which one is perpendicular? R is the perpendicular. So write R by root over of R square plus H square, that is equal to 1 by mu. Then cross multiply and take a square on both sides. It will be mu square R square equal to R square plus H square. So take this R square on that side, so it will be taken common. R square equal to H square. So R will become H by root over of mu square minus 1. This is the answer of the radius of the circular patch. Sometimes it is said that calculate the area of that circular patch. Just calculate pi r square after this calculation. Okay. Sometimes radius is asked, sometimes they ask for the calculation of the area of the patch. This problem is called the fish eye view problem, because if you consider a fish whose eye is at this point, then this fish can see the outside world just through a circular patch formed on the water surface. Remaining portion of the water surface, he cannot see the outside world. So that's why this is called fish eye view. Okay. Now we will discuss one or two problems on this. One problem we will mainly focus. This is a infinitely long cylinder, glass cylinder, or any opaque material. You may not consider it is glass. Any transparent material cylinder. Okay, any transparent material cylinder. Clear? Solid cylinder. Now, we consider this one is the axis. Okay. Light is falling on this at an angle of incidence. This is the normal. Light is falling at an angle of incidence I. outside medium is air, refractive index is given 1, and this cylindrical material have refractive index mu, which is greater than 1, means cylinder is the denser medium. Okay. Then the light is falling on the flat surface, one of the flat surface of the cylinder, and enters the cylinder. Then the light ray will fall on the curved surface of the cylinder. Okay. In which condition the light ray cannot come out from the curved surface of the cylinder? So for that you have to find out the range of angle of incidence for which the light ray entering the cylinder cannot come out from its curved surface. Because this one is a cylinder, suppose light falls on the top surface is flat surface, light falls on there and suffers a refraction, goes inside. Then the inside light strikes the curved surface, and the condition says that through this curved surface light cannot come out to the air medium again. Then what should be the range of this angle such of incidence on the flat surface such that light ray cannot come out to the curved surface? That you have to calculate. See, this problem can be given in different way. Suppose 4 options are given, what is the correct range for I? Then it will be MCQ and you may face this type of problem in the exam.
Greater than say.
Mm-hmm.
Greater than critical angle. I should be greater.
No. The angle of incidence on the curved surface should be greater than or equal to critical angle. For that, what will be the range of I? That you have to find out.
It should be less than critical angle.
There is a relation that you have to find out. For it. I should be less than equal to sine inverse root over of mu square minus 1. This form you have to derive. Because sometimes in the exam 4 options are given. Sine inverse mu, sine inverse root over of mu square minus 1, greater than or less than, this type of formulas can be, expressions can be given. You have to choose the correct option. See, the main thing is in the drawing, not in the calculation. You have to draw the light path properly. Otherwise, you cannot solve the problem. ray, refracted ray will incident on the curved surface. Then through the curved surface it will try to come out, means another refraction is going to happen. But you have to find out a condition for eye such that through that curved surface light cannot come out. Okay. Then I consider that through this point light is entering like this. Okay. It suffers a refraction. Angle of refraction is considered as R. Then on the curved surface I consider another normal at this point, and this angle is considered as, say, I2. Angle of incidence of the light ray on the curved surface is considered as I2. Now two conditions can happen. I can write I2 greater than equal to critical angle. Then the light ray cannot come out from the curved surface. Because if I2 is just equal to critical angle, the light ray will follow this path. Means it is parallel to the surface. And if I2 is greater than critical angle, this will suffer total internal reflection. In critical angle, it will be parallel to the surface. If it is greater than critical angle, then it will reflect back. Okay. So the condition for light not to come out from the curved surface is angle of incidence at the curved surface should be greater than or equal to critical angle. Clear? So I put this. Now the thing comes. Extend this normal. This angle will be 90 degree. Okay. Then can I write I2 plus R equal to 90 degree? Because that is a right angle triangle. So if one angle is right angle, then other two angles terms should be 90 degree. Then I2 can be written as in that equation. I can replace I2 by 90 minus R. Replace it. 90 degree minus R greater than equal to theta C. (90 minus R) greater than equal to theta C. Take sine on both sides. Sine 90 minus R greater than equal to sine theta C. What is sine 90 minus R? Cos R. Cos R greater than equal to sin theta C. But what is sin theta C? 1 by A. Okay. And cos R is greater than equal to 1 by mu. Now come back to Snell's law. Light is traveling at the first interface on the flat surface. Light is traveling from air to cylinder. So rarer to denser. Air has a refractive index 1. Cylinder has a refractive index mu. So sin I by sin R equal to Can I write sin r equal to sin I by mu? Then sin square r will be equal to sin square I by mu square, squaring both sides. Sin square r can be written as 1 minus cos square. Now from that calculate cos r. What is the value of cos r? Calculate from this. Means expression for cos r. This term on that side. So it will be mu square minus sin square I divided by mu. Its root. Check. I write the direct form. Calculate and check whether it is coming or not after taking the square root. I jumped 1 or 2 steps. Up to this, it is clear. 1 minus cos square r. Then calculate from this to find the value of cos r and see whether it is coming or not. Check. I write directly. Coming? Now put this value of cos r here. Put this value of cos r in that inequality. So it will become root over of mu square minus sin square I divided by mu greater than equal to 1 by mu. So this mu's will cancel. Okay. Mu's will cancel.
So we can take square root on both sides.
Square root, no. Square on both sides. Then it will be mu square minus sin square I greater than equal to 1 after taking square on after this step. Mu square minus sin square I greater than equal to 1. So we can write sin square I less than equal to mu square minus 1. Sin square I will be less than equal to mu square minus 1. So I less than equal to sin inverse, not here, somewhere else, here. So it will be I less than equal to sin inverse root over of mu square minus 1. See, this final step, this one, you have to remember. Okay, because if this problem comes with the final step, if you remember directly, you can take the correct answer. And if you remember this final step, some additional questions can be solved very easily from this step. Okay. Now, three questions I will tell you. First question is that, okay, fine. At this point, suppose total internal reflection occurs. So light ray cannot come out through this surface, this point, through this curved surface it cannot come out. Then the light ray goes along this, strikes here. Can it come out from this point after striking here? Once it cannot come out from the curved surface, then it can never come out from the cylinder. Can you tell me why? In the first encounter with the curved surface, if it cannot come out, then it can never come out from the curved surface. Whatever be the length of this, how many total internal reflection it may suffer, no matters. If for the first time you can stop the light to come out from the cylinder, then never this light ray will never come out from the cylinder. Why? Because this will suffer total internal reflection at this point if this I2 is greater than critical angle. And in total internal reflection, law of reflection is obeyed. So this angle should be I2. Then that light ray will strike here. But again, due to alternate angle, this angle is again I2. And once you consider here I2 is greater than critical angle, then for all encounter with the cylindrical surface, angle of incidence is greater than critical angle. So at all the surfaces, at all, everywhere it strikes at an angle greater than critical angle. As a result, it cannot come out. Once it is trapped forever. This is the principle of optical fiber. This is the principle of optical fiber. Once the electromagnetic wave enters the optical fiber, it is trapped inside the optical fiber. And technique is used in optical fiber communication. And since on all the refraction with the curved surface, total internal reflection will occur. That's why in the optical fiber electromagnetic energy is almost preserved, because no refraction is there. So energy cannot come out. Energy is trapped in that medium. Okay, so this is the first question. Next question. I consider first time this one outside medium is there. Okay, I consider this cylinder is made with glass. And second time I will consider an hypothetical case. This cylinder is suppose made up with water. Suppose made up with water. Outside medium in both the cases are air. What will be the possible values of angle I? That range. What will be the possible range? That formula we have already calculated. So if I provide you the value of mu, you can find the I for me. Just calculate. First case, consider a cylinder prepared with cylindrical material is actually water. Water cylinder, suppose its shape is remains same. It is not falling or anything. Hypothetical experiment. So first consider mu equal to 4 by 3. Right? Mu equal to 4 by 3. Outside medium is air. That is one. And in the second case, consider cylinder is made with glass having refractive index 1.5 and calculate the range of I again in both the cases. Calculate. For glass, refractive index 1.5. For water, refractive index 4/3. That final formula, I less than equal to sin inverse root over of mu square minus 1, you have to put the two different values of mu to calculate the range of I in both the cases. Just keep it in sin inverse form. Otherwise, calculator is required. Calculator, you have you cannot use calculator. Write it in the sin inverse form. What is coming for water? Sin inverse of
Root 7/3.
root 7/3. For water is coming I less than equal to sin inverse of root 7/3. 3 inside root. 3 is outside root. Okay. And for glass, sin inverse
Root 5.
root 5/2. Now, is there any discrepancy in the result? First one is using water cylinder, second one is using glass cylinder. Is there any discrepancy in any of the results? Between these two calculations, one is a valid calculation, other one is an invalid calculation. Check the result carefully. One of the result is invalid. That cannot happen in reality. That is a valid result. Tell me root 7, whether the value of root 7 is greater than 3 or less than 3? Less than 3. So sine inverse of a value less than 1, that is possible. Second one, using the class, root 5 by 2, root 5 has a value greater than 2. So sine inverse value is coming greater than 1. Sine function's range is from -1 to +1. It cannot exceed +1. If you calculate root 5 by 2, its value is greater than 1. Sine inverse 1 is not possible. So this second calculation is not possible, means using glass cylinder you cannot trap the light ray. If the light ray is coming from air to glass, then you cannot trap. But if the light ray is traveling from air to water, then you can trap by this method, because that is giving a possible angle. Because this value, sine inverse of root 7 by 3 will give you a valid angle. But sine inverse of root 5 by 3, if you put in calculator, it will give us error. Because sine inverse means the value should be less than +1. It cannot exceed +1. Okay, the range of sine function you know. Because sine theta -1 less than equal to sine theta less than equal to +1. Value of sine theta cannot exceed +1. Okay, so this calculation with the glass cylinder, it is not valid. Now, so it shows that for all value of mu, taking different material, for all value of mu you cannot find this angle for trapping the light ray, because glass cannot trap the light ray. Similarly, water can trap. Then what should be the range of mu such that you can trap the light ray? You can find it directly from this formula, because this formula is valid only when this mu square -1 root will give you a value less than equal to 1. Because in that case, sine inverse of less than equal to 1 you can find. Sine inverse of a value greater than 1 is not possible. Okay. So necessary condition for this to occur for trapping the light ray would be root over of mu square -1 less than equal to 1, which shows that sine theta means sine I less than equal to 1. And from this you can find out, taking a square on both sides, mu square -1 less than equal to 1. So mu, right here, mu less than equal to root 2. Mu less than equal to root 2. In that case, you can only trap when the light ray is traveling from air to other medium. Mu should be less than or equal to root 2. Now check, root 2 means roughly 1.41. When I give glass has a refractive index 1.5. 1.5 is greater than root 2, so glass cannot trap. Air is 4 by 3, nearly 1.33. So 1.33 is less than root 2. So water cylinder, when light is traveling from air to water, it can trap. Okay. So sometimes this problem comes directly, that what should be the range of mu to trap the light ray. So mu can direct, or what should be the maximum value of mu that you can consider for the cylinder for which light can be trapped. It will be root 2. Directly you can, if you remember this one, you can find the answer. But provided outside medium should be air. If you change the outside medium, then again the ratio will change. Then the values will change, all these things. I here discuss for air. Okay. No. Suppose this one is an interface of the two medium. I consider this medium is air. This medium is glass. And I consider this is the normal. A monochromatic ray is falling at this point. At any angle of incidence. One part of this ray is reflected. One part of this ray is reflected. Okay. And another part of the ray is refracted. Reflected, refracted. And it is said that reflected and the refracted part light rays are perpendicular to each other. Reflected and the refracted rays are perpendicular to each other. Then what is the angle of incidence? Four options are given. Sin I, sin inverse mu, B cos inverse mu, C tan inverse mu, D none of these. It is falling on the interface. A part of light is reflected and another part is refracted. It is given that reflected and the refracted rays are perpendicular to each other. Then what is the value expression for angle of incidence? means this angle I. What is the expression for I? That you have to find out. And refractive index of glass is given mu. Refractive index of air is 1.
So, since reflection is also happening, will I equal to R? Will angle I equal to angle R?
But angle of refraction is different. It should be taken R prime or anything.
Option C.
There is a special name for this angle of incidence. This will come in polarization also. Angle of polarizing angle or Brewster's angle. From the Snell's law, you can derive the answer. See, this angle of incidence is taken as I. So I consider this angle of reflection. That is also I. Because angle of incidence and angle of reflections are equal. Only the angle of refraction is different. R. Okay. Then consider the sum of these three angles. First one is I, second one is 90 degree, third one is R. Total is 180. This I, this 90, this R will become 180. So I can write angle R equal to 90 minus I. So it shows that angle of incidence and angle of refraction are complementary angles to each other. Because R equal to 90 minus I. Then apply Snell's law. Sin I by sin R, that is equal to mu. Then it is sin I by sin 90 minus I. Sin 90 minus I. But sin 90 minus I is cos I. Sure? Sin 90 degree minus I. that is equal to cosine from complementary angle. So it will become sine angle cosine. That is tan phi. So I equal to tan inverse of mu. That is the correct answer. Okay. Now, I will ask you one question, that is dispersion of light. If I ask you what is dispersion of light?
Splitting of this.
Louder. Tell me, what is dispersion of light?
Splitting of white light.
Splitting of white light. How?
Where it passes through a prism.
So shouldn't I write splitting of white light into its component colors while passing through a prism is called dispersion of light?
Yes, sir, because a monochromatic light cannot.
But is this definition correct? What I said? No. Splitting of white light into its component spectrum or component color is the dispersion of light. That is the correct definition, what you said at the beginning. Whenever you will see this picture of the dispersion of light, 7 component colors in the book, you will find a prism. But prism is not necessary for producing dispersion. Prism is necessary for seeing all the spectrum of white light clearly. That is called a pure spectrum. Otherwise, if there is a single refraction and from which dispersion will occur, in that case you can see only 3 to 4 colors, because many colors will overlap and you cannot see them. That is called impure spectrum. Okay. And the only reason for dispersion of light is the refraction. Only reason for dispersion is refraction actually. Okay. Now, on the basis of Snell's law, we can explain the splitting of the white light into different spectra. Prism is not at all necessary for producing dispersion. For getting a pure spectrum such that we can visualize all the 7 spectrum properly, prism is required. Because in prism, how many refraction will occur? 2. And both refraction and prism produces angular deviation such that the total angular deviation will increase. Previously, suppose after single refraction, 7 colors are occupying in this small amount of position. Then after 2 successive refraction in prism, they are occupying within this region. So each color will occupy separate space. Previously, in this small portion, some colors will overlap with each other and you can see only 3 to 4 colors. So that's why that spectrum is called impure. Prism is necessary only to produce pure spectrum, not for producing dispersion of light. If there is a change in medium, that is the refraction will occur for polychromatic light or white light, definitely dispersive spectrum you can see. It may be 3, 4, may not be 7, but still dispersion will occur. So this is a wrong belief of the student that prism is required or the light should pass through the prism for producing dispersion. That is totally wrong. Light should suffer refraction. Polychromatic light or white light should suffer refraction. That is essential. Okay. So in the next class we will discuss the dispersion and the prism portion, because a vast portion of the geometrical optics with refraction is used is devoted to the refraction through prism for monochromatic light and white light. When we discuss monochromatic light, we discuss the necessary derivations and all these things. Then we use the polychromatic light's refraction through the prism, which will produce pure spectra, and dispersion effect on all these things we can discuss. Okay. Where is its switch? Oh, okay. Okay. So we will discuss the other part of the geometrical optics, that is prism. Switched on. Hello. Okay. So we will discuss the prism portion of the refraction of light. First we consider the refraction of a monochromatic light through a glass prism. This one is a structure of a glass prism. And we consider that a monochromatic light is falling at one of the surface of this glass prism. Let us consider this one is that monochromatic light. Okay, so when the monochromatic light is incident on that surface, we consider that when enters into the glass medium, light ray will bend towards the normal like this, and then it will strike this interface and again bends away from the normal. Now for these two portions, if I draw to normal at this point of incidence, we can say that in the first refraction the light ray is traveling from rarer to denser, so it will bend towards the normal. In the second refraction the light ray is traveling from denser to rarer, so it will bend away from the normal. Okay, now this angle is considered as the angle of incidence at the first surface. This one is the angle of refraction for the first surface, This one is considered as the angle of incidence for the second surface, which is denoted as R2. R2. And finally, this angle is denoted as I2. It is the angle of refraction for the second surface, which is generally called angle of emergence. Okay, so inside the prism, two angles formed, those are considered as R1 and R2. R1 is the angle of refraction for first surface, whereas R2 is the angle of incidence for the second surface. R does not always mean angle of refraction. R1 is angle of refraction for the first surface, whereas R2 is the angle of incidence for the second surface. Here I1 is the angle of incidence at the first surface, I2 is the angle of refraction at the second surface, which is generally called angle of emergence. Okay, now, so what happened to the path of the light ray due to the introduction of this prism? Due to the introduction of the prism, the light ray actually deviates from its path, and after two successive refraction, prism bends the light ray towards its base. See, this is the base of the prism, and after two successive refraction, this light ray is bending towards the base of the prism. Okay, now we want to find out the angle of deviation produced in the path of light ray by this prism. Angle of deviation in the path of light ray produced by the prism. So we consider that if there will be no prism, this light ray will follow this path, and due to the introduction of the prism, this light ray is actually following this path. So this angle is termed as delta. This angle is termed as delta, means if there is no prism, light ray will follow straight along the straight line path. Due to the introduction of the prism, after two successive refraction, light ray follows this path. So angle between these two is called the angle of deviation. Okay. Now, in the first refraction, light also deviates a little bit. What is the deviation produced in the path of light ray in the first refraction? See, this one. Call it delta 1. Refraction produced at the path of the light ray in first refraction is delta 1. Deviation produced in the path of light ray due to second refraction is delta 2. Check, this one is the deviation produced due to first refraction. This is the deviation produced in second refraction. And see, we can write total deviation delta equal to sum of the two deviations. Delta equal to delta 1 plus delta 2 from the theorem that in sum of the two opposite interior angle equal to exterior angle. So from that we can write delta equal to delta 1 plus delta 2. Now, what is delta 1? From this diagram we can see that delta 1 means I1 minus R1. I1 minus R1. Similarly, delta 2 means I2 minus R2. I1 minus R1 is delta 1, I2 minus R2 is delta 2. Then you can write this one as I1 plus I2 minus of R1 plus R2. Right. R1 plus R2. Now suppose a prism is given, a monochromatic light source is given, and you complete this experiment. And you have to measure the delta. I1 given, I2 you can, I1 we can measure by some apparatus, I2 we can measure by some apparatus, then we have to measure R1 and R2 by using the apparatus which measures the angle to find delta. But see, it is impossible for us to measure R1 and R2 by using any apparatus. Why? Since these two angles are formed inside prism, so you cannot insert any device inside the prism to measure these two. That's why sum of R1 and R2 can be calculated from the geometry of the prism. And sum of R1 plus R2 equal to capital A, the angle of prism, this one, capital A. Now, using a little bit of geometry, you can prove this. If I extend this normals, they suppose intersect at an angle theta. Inside this angle is considered as theta. Okay. Then you can consider this small triangle formed at the bottom, and from this you can write here R1 plus R2 plus that theta equal to 180 degree. Okay, R1 plus R2 plus theta, that is equal to 180 degree, implies R1 plus R2 equal to 180 degree minus theta. Now come to this quadrilateral, this point, this point, this one, this one. So in this quadrilateral you can see that one angle is 90 degree because this is the normal. This angle is also 90 degree because that is also a normal. So we can write 90 degree plus angle A plus another 90 degree plus angle theta. This sum should be 360 degree because sum of the four angles of a quadrilateral is always 360 degree. Now two angles of the quadrilateral, one is capital A, one is theta. Remaining two angle means these two black lines are actually normal. Normal means they are forming angle 90 degree each. So two angles each of 90, one angle A, another angle theta. Then we can also write capital A equal to 180 minus theta. It shows that both of these are equal. So R1 plus R2 sum can be written as capital A, and inserting this you can write this form of delta, that is delta equal to I1 plus I2 minus capital A. I1 plus I2 minus capital A. Okay. So this is the deviation produced by the prism. So if you know angle of incidence, angle of emergence, and you know the angle of prism, then you can find the deviation of the light ray. Okay, now we will consider a situation that what can be the minimum value of the angle of incidence. What can be the minimum value of angle of incidence I1? That is always 0 degree. Means when the light ray is falling along the normal, then angle of incidence I1 will become 0 degree. Now what will be the maximum value of the angle of incidence? Almost 90, like this. So when the light ray is going like this almost, then angle of incidence has a maximum value 90 degree. Now let us consider that from minimum value of the angle of incidence, that is 0 degree, I increase the angle of incidence in small steps. So I1 is increased from 0 to 90. What is the variation in delta? Will it increase as I1 is increasing, or will it start to decrease as I1 is increasing? We are going to increase I1. Suppose I1 is initially 0 degree, then 2 degree, 3 degree, 4 degree, 5 degree. In this way, we want to increase I1. What will happen to delta? Will delta increase or will delta decrease? Increase. Okay. Same. Any other? Fast decrease and then increase. Okay, because you know that there is a phenomena called minimum deviation. So when you start to increase I1 from 0, initially the delta will start to decrease. It will reach a minimum value, then all of a sudden it start to increase. Suppose from 0 to 35 degree, let us consider an example, 0 to 1, 2, 3, 4, 5, 6 onwards, and then suppose up to 35 degree value of I1, delta will decrease. And then when I1 crosses 35, further increasing, delta starts increasing. So it reaches a minimum value. So the curve looks like this. If you plot a graph between delta and I1, the graph looks like this. So it shows that there exists a minimum value of delta, which is termed as the delta M, minimum deviation condition. For a particular value of I1, it will become minimum and then again starts to increase. Okay. So initially I1 increasing, delta decreases, then it reaches a minimum value, then I1 increases, delta starts increasing. Now, what will be the condition at which delta reaches this minimum value? That is I1 equal to I2. When angle of incidence and emergence will be equal, then delta will have its minimum value. But how? See, from this expression, I can write this expression as root I1 minus root I2 whole square plus 2 root I1 I2 minus capital A. This delta can be written as root over of I1 minus root over of I2 whole square plus 2 root I1 I2 minus A. Just check, calculate all this term. First term will be root I1 square, means I1. Second term will be root I2 square, that means plus I2. Next term will be 2 root I minus 2 root I1 I2. This 2 will cancel, then minus A. Same term, but written in a different format. See, now if I change I1, only minimum value of this delta occur when this whole square term will have its minimum value. So real number whole square, what will be its minimum value? 0. If there is a real numbers whole square, its minimum value can only be 0. So for delta to be minimum, this whole square term should be 0. So for delta to be minimum this I1 should be equal to I2. If you get this whole square term equal to 0, then root I1 equal to root I2 means I1 equal to I2. And in that situation, I can write both these angles equal to I. And then from this formula, we can write delta minimum equal to, this term is 0, this is 2 root I square, means 2I minus A. That is the formula for minimum deviation. Delta M equal to 2I minus A. This property you have to remember, that any real numbers whole square must have a minimum value 0. It cannot be negative, because if whole square term is negative, then it shows that the number is imaginary. So delta M equal to 2I minus A. Okay. Now, in this situation, when I1 equal to I2, R1 is also equal to R2. I1 equal to I2 means R1 and R2 both are same. And in that situation, we can write R1 equal to R2 equal to R, which is equal to A by 2. Because earlier we write that R1 plus R2 equal to capital A, but if R1 is equal to R2, then we can write both of these equal to R. Then R1 plus R2 means 2R. 2R equal to A. So A will become, R will become A by 2 in this minimum deviation. And another property, the path of the light ray inside the prism, this part. When minimum deviation condition is reached, path of the light ray inside the prism will be parallel to its base. This is a property of minimum deviation. Because I1, I2 are equal, R1, R2 are equal, so the light ray path inside the prism will be exactly parallel to the base. In other angles, when minimum deviation is not reached, this path of the light ray and the base of the prism are not exactly parallel. Only in minimum deviation these two lines are parallel to each other. Okay. Done? Next, for that prism, remember that diagram. In minimum deviation condition, I can write sine I by sine R that is equal to mu for the first surface. Sin I1 by sin R1 that is equal to mu, but in minimum deviation I can consider that I1 equal to I2 equal to I, R1 equal to R2 equal to R, so I can write without suffix 1 that sin I by sin R for first refraction will be mu. Now we have derived in minimum deviation condition that delta M equal to 2I minus A. So from that I can write I equal to delta M plus capital A by 2, delta M plus capital A by 2, and sorry, this one is so we can write I equal to delta M plus A by 2, and we earlier write that R equal to A by 2. So we can find a simple formula for mu of the refractive index of the prism, that it is equal to sine delta M plus A by 2 divided by sine A by 2. Okay. Right? Okay. Write down one problem. For a prism, when a write down through a prism, when a monochromatic light passes, it is found that angle of minimum deviation is equal to the angle of prism. Angle of minimum deviation is equal to the angle of prism. Okay. Find the value of angle of prism. If refractive index of the material of the prism is √3, refractive index of the material of the prism is √3. You have to find the value of capital A. And delta M is equal to capital A. It is given that angle of minimum deviation is equal to angle of prism. use that formula mu equal to sine a plus delta m plus a by 2 by sine. Okay. Now we will discuss two problems. Both the results you have to remember only, not the entire derivation, only the results you have to remember. First one, suppose this is a prism. Monochromatic light ray is incident on the first surface of the prism. Light ray enters this medium. Okay, little bit deviated. Draw. The condition says that after falling to the second surface, light ray will not come out from the second surface. It either suffers total internal reflection at the second surface or goes along the interface, means at critical angle. It will fall. Either parallel to the second surface or suffer total internal reflection from the second surface, it cannot come out. Then what will be the range of angle of incidence that you have to find out? Same to the previous problem that we have discussed in the morning session, that is with the glass cylinder we consider. Here it is with prism. Now check carefully. I can consider this is the normal at the point of incidence. So this angle is I1, this angle is R1. Then this is the normal drawn at the point of incidence. This angle is R2. Now remember, if R2 is greater than equal to critical angle, then I can consider that no light ray can come out from the second surface only. If it is equal to critical angle, then light ray grazes along the interface like this. Or if it is greater than critical angle, then light ray suffers total internal reflection and trapped inside the prism. It cannot come out from the second surface. So only condition is that R2 greater than critical angle. Now I have to find out the range of I1. So R1 plus R2, I add R1 on both sides. Okay, so we can write R1 plus R2 greater than equal to R1 plus theta c. To this inequality I add R1 on both sides. Now what is R1 plus R2 for the prism? Capital A, this angle. So I can write here, this is capital A greater than equal to R1 plus theta c. Okay, R1 plus theta c. Then can I write R1 less than equal to A minus theta c? R1 less than equal to A minus theta c. Okay, then I will apply sine function on both sides. That is sine r1 less than equal to sine of a minus theta c. Sine a minus theta c. Then I will write one more line here, that is sine r1 less than equal to sine a minus theta c. You can write it as sine a cos theta c minus cos a sin theta c. Using the formula of sine a minus b, I can write it as sine a cos theta c minus cos a sin theta c. Okay. Now we already have sin theta c. What is sin theta c? 1 by mu. Then can I write this one as, for the first surface I apply Snell's law. Snell's law says sin I1 by sin R1 equal to mu. So what is sin R1? Sin I1 by mu. So in place of sin R1 I write sin I1 by mu. This is less than equal to sin A into root over of 1 minus 1 by mu square minus cos A into 1 by mu. In place of sin theta c, I write directly 1 by mu. Cos theta c means root over of 1 minus sin square theta c, because sin square theta plus cos square theta will be 1. So I write 1 minus sin square theta c, that is 1 by mu square in place of cos theta c. Okay. Then sin I by mu less than equal to sin A into root over of mu square minus 1 divided by mu. I can write this term cos A into 1 by mu. Check. This one, take the LCM, mu square minus 1 by mu square. So it will be root over of mu square minus 1, and root over of mu square means 1 mu will come out. See, all the term containing 1 by mu in the denominator, there is a mu, so I can cancel that mu and write I1 less than equal to sine inverse of very large value, root over of mu square minus 1 into sine A minus cos A. This one. This is the range of I1. I1 should be less than this value. So if you know the angle of prism and refractive index, then from this you can find a value of I1. Then this value of I1 is the maximum value, and if I1 is less than equal to, then light cannot come out from the surface. So the value of I1 should be greater than this, such that light can come out from the second surface. So if it is equal to this value or less than this value, then light cannot come out, because equality implies that the angle of refraction R2 at the second surface, the angle of incidence R2 will be critical angle, and if you are considering less than, then it is greater than critical angle, R2 will be greater than critical angle, and light cannot come out. So only case is that when light ray can come out from the second surface is I1 should be greater than this value, and if it is equal to or less than this, then light ray cannot come out from the second surface. So you have to remember this last formula, only this part, for solving problems. No need for the detailed derivation, you can remember only this final form. Another problem is there whose result is much more easy to remember, but it is more logically rich problem. So I will come to the entire logic and then finally I will mention the formula which you have to remember for your exam. Okay. Next, let us consider a prism. Any light ray is falling, monochromatic light ray is falling on the prism. It enters the prism and it says that no light ray can come out from the second surface. Like this. Here we can consider R1, here we can consider that is a normal, so it is R2, it is I1. Now the question is that angle is A, refractive index of the material of the prism is given mu. First write down the question. What is the relation between mu and capital A? What is the relation between mu and capital A such that no light ray can come out from the second surface of the prism? No light ray can come out from the second surface of the prism, irrespective of its angle of incidence. Irrespective of its angle of incidence. So only a relation between A and mu is required such that no light ray can come out from the second surface. See, what is the difference from the previous problem? In the previous problem, there are certain values of the angle of incidence I1 for which light can come out from the second surface. One range is there. I1 less than equal to some value, means I1 having value greater than this can come out from the second surface. Now this one is a peculiar problem. It says that whatever be the angle of incidence, the light ray can fall on the first surface. Light cannot come out from the second surface. There is no chance of coming out. Light ray falling on the first surface, entering the prism, but there is no such condition. Any light ray which enters the prism cannot come out. So it is different from the previous problem. Previously there is a certain region in which light can come out. Here it is asking for a condition in which no light ray can come out, means its angle of incidence can be between 0 to 90 any value. I1 can be between 0 to 90 any value, but no value of I1 helps the light to come out from the second surface. Then this condition, how to derive? So for this I first want to ask you two questions. What is the value of angle of refraction if angle of incidence is 0 degree? Not for a prism, for any surface. What is the value of angle of incidence if in rarer medium, then in denser medium, angle of refraction will become 0 degree. Angle of incidence 0 in rarer medium, then what will be the angle of refraction in denser medium? 0. Sin I is 0 means R is 0. So light ray falls normally, will go straight. Right? Now, what is the maximum value of angle of incidence in the rarer medium? 90 degree. Now tell me, for angle of incidence 90 degree, what will be the value of angle of refraction in the denser medium? Let us consider this one is an interface. Angle of incidence 0 degree. Light falls straight, goes straight. So I0, R0. Now you consider that angle of incidence has a maximum value 90 degree. So if the angle of incidence is 90 degree, means light ray is falling parallel to the interface. Then if this light ray enters into the denser medium, then what will be its angle of refraction? That I want to know.
Less than 90, sir. Less than 90 degree.
Now I want the exact value.
30.
Critical angle. Correct. See. Check this one. If it is denser medium and it is rarer medium, it is the interface. Any monochromatic light ray falling at critical angle, falling at any angle, first we consider, say I, it will bend away from the normal. This one is R. Now remember, there is a principle which is called the principle of reversibility of light path, which says that if you change the direction, the path of the light will remain same. Means this is angle of incidence in the denser medium, this is angle of refraction in rarer medium. If you change the direction of the light ray, means instead of sending light from this, you are sending light along this, then this R will be the angle of incidence in the rarer medium and this I will be the angle of refraction in the denser medium. Just position of I and R is reversed. If you change the direction, path of the light will remain same. Okay. Using this logic, we can say that what happens in case of a critical angle. This is the interface. Let us consider this light ray is falling at an angle equal to critical angle. Angle of incidence is now critical angle. Then light ray will be parallel to the interface. So I equal to theta c, R becomes 90 degree. Now uses that principle of reversibility. Light goes like this. So angle of this one becomes the angle of incidence. So as this becomes the angle of incidence 90 degree, it will follow like this. So angle of refraction will become critical angle, because I and R, they are reversed. See, when light comes from denser to rarer, this is I, this is R. Angle of incidence, angle of refraction. If I change the direction of the light ray, this R will become angle of incidence and I will become angle of refraction. Similar to this I equal to theta c is the angle of incidence and light is parallel to the interface, so we consider that angle of refraction becomes 90. We apply the reversibility and say that this will follow the same path, then this one is the angle of incidence, it becomes 90, and angle of refraction becomes this one is equal to critical angle. So whenever in a rarer medium angle of incidence becomes 90 degree, then in the denser medium light ray will have a angle of refraction equal to critical angle. Just see the situation, this is denser, this is rarer. When you say that light is coming from denser to rarer, how to define critical angle? Angle of incidence is equal to critical angle, angle of refraction becomes 90 degree when light coming from denser to rarer. Now I am saying that light is going at an angle 90 degree, angle of incidence in the rarer medium. So in the denser medium it will refract at an angle of refraction critical angle. Just the reverse phenomena. Principle of reversibility of light. Very important point. Many logics can be explained on the basis of this. Okay. Now, so first we consider what is the condition for no emergence from the second surface, that we know, that is R2 greater than equal to theta c. This is the condition that has to be fulfilled, that R2 greater than equal to theta c, that is true. Okay. Then consider what is the maximum angle of incidence on this first surface. I1 should be 90. In that case, what will be the value of R1? We have derived here. If I1 is 90 degree in the rarer medium, then inside the prism in denser medium, the angle of refraction R1 should be equal to critical angle, as the principle of reversibility suggests. Then I can write for this particular angle, that is if I1 equal to 90, then R1 should be equal to theta c. R1 90 is the maximum value of angle of incidence. Angle of incidence cannot be greater than 90 because it is from 0 to 90. So 90 is the maximum value. So I calculate only for the maximum value. Then I can write R1 plus R2 greater than equal to R1 plus theta c as before. I add R1 on both sides. But see, what is R1 plus R2? But R1 for this particular case I consider so the relation comes A should be greater than 2 theta c and A greater than equal to 2 sine inverse 1 by mu. That is the relation between A and mu. So prism angle, so whenever the angle of prism is given and mu is given, check 2 sine inverse, whether angle of prism is greater than 2 sine inverse of 1 by mu or not. That is 2 times greater than the 2 times of critical angle or not. That means if this occurs, then no light can come out from the second surface, whatever be the angle of incidence. Now I will ask you only one question, last question. On this formula you have to remember, these 2 steps. Sometimes from these two steps MCQ will come. What is asked in the question? Light ray cannot find a relation between A and mu such that light ray cannot come out from the second surface irrespective of its angle of incidence. Means whatever be the angle of incidence, it cannot come out. And here I derive the relation by considering the angle of incidence to be 90 degree, that is maximum. Who can say that if angle of incidence is less than 90 degree, then light ray will not come out from the second surface? I haven't checked that. I consider only for the maximum value of I1. For maximum value of I1 it is coming. But is there any guarantee that if for maximum angle of incidence light cannot come out from the second surface, then for all other angle of incidence less than 90 it cannot come out from the second surface? I haven't checked that. Is there any argument by which you can say that if for maximum angle of incidence 90 degree it cannot come out, then for no angle of incidence it can come out? Okay, fine. Let us consider any angle of incidence less than the maximum value, that is less than 90. Suppose say 40 degree or 60 degree. Okay. So if the angle of incidence is less than 90, then angle of refraction R1 is less than critical angle. It is less than critical angle. Then R2 should be greater than, much more greater than the critical angle. Why? Check. For I1 90 degree, R1 becomes critical angle. So if I consider I1 is less than 90, then R1 is less than critical angle. But we know that R1 plus R2 equal to, so for 90 degree I consider the angle is R2 is greater than or equal to critical angle, but R1 plus R2 remain fixed. So if R1 decreases from critical angle, then to keep this sum fixed, R2 should increase. So if 90 degree R2 is already greater than critical angle, then if this one is decreases than critical angle, then this one will be increased much more than the previous value. So no light ray can come out. So for 90 degree for I1 90, R1 is equal to critical angle. I1 90, R1 critical angle. R2 is equal to critical angle or greater than that. Now we are decreasing I1. As we are decreasing I1, R1 will also decrease from the value of critical angle. Since R1 decreasing, R2 should increase, because R1 plus R2 sum should be fixed. So R2 should increase. So you are already considering R2 is greater than critical angle. Now if R2 increases further, it is always greater than the critical angle. So no chance for the light ray to come out. Because if it happens that you decrease R1, as a result R2 decreases.